In this video, we're going to look at applying Le Chatelier's principle to predict the effects on the yield of a reactant or product when we change the concentration, pressure, or temperature. We're going to start by revising what an equilibrium process is. We're now going to look at a special kind of reversible reaction called an equilibrium. An equilibrium is when a reversible reaction takes place in a closed system. And a closed system means that no reactants or products can get in or out. So for example, if you're doing this inside a conical flask and you put a lid on the conical flask, you'd have then changed it into a closed system because nothing could get in or out. In an equilibrium, the concentration of the reactants and the products remain constant. So that means those concentrations don't change once we reach equilibrium. And the rate of the forwards and the backwards reactions are the same. So this means we produce both the products and reactants at the same rate. So let's look at an example to help us visualize this process. So let's look at a general equilibrium, A and B reacting together to make C and D. Now remember, C and D can also react together to make A and B again. So in our closed reaction vessel, you can see we've got some A and B chemicals and some C and D chemicals. Now it doesn't matter that we've got different amounts of each, you won't always have the same numbers of each at equilibrium, but we're going to look at what happens now we can say this is at an equilibrium. So in this equilibrium, the concentrations of the reactants and the products is going to remain constant. That means during this equilibrium, we should always have 2 A's and 2 B's, and 3 C's and 3 D's. The amounts of those shouldn't change because they're remaining constant. And the rate of the forwards and backwards reactions must be the same. And this is why the concentrations remain constant, as we're going to look at now. So what this means is that every time an A and B react together to make a C and D, a C and D will react together to make an A and B. So both reactions, both the forwards reaction and the backwards reaction, happen at the same rate, so the concentrations remain constant. We've still got 2 A's and 2 B's, and 3 C's and 3 D's. Le Chatelier's principle states that if the conditions of an equilibrium are changed, the system will shift the position of equilibrium to counteract the change. Now we're going to break down what that means, but basically if we make a change to an equilibrium, for example if we increase the temperature, the system will try to do the opposite, so in that example it would decrease the temperature. If we try to decrease the pressure, the system will try to increase the pressure. So we're going to look at how the system does that. So for our general equilibrium again, A and B making C and D, let's just say the position of equilibrium at the moment is in the middle. If we say the position of equilibrium shifts to the left, this means we're going to make more of everything on the left-hand side of the equation. So if we say we shift the equilibrium to the left, that means we're making more A and B, and we're going to make less C and D. If we say we're shifting the position of equilibrium to the right, what that means is we're increasing the amount of C and D that we make, and we're decreasing the amount of A and B that we make. When we're talking about equilibrium, we'll commonly use the term yield, and this means the amount that we've made. So for example, for this equilibrium, if we shifted the position to the right, this means we're going to make more C and D. So we could say we've increased the yield of C and D because we've made more. Because we're making more C and D and less A and B, we could say that we have decreased the yield of A and B. Adding a catalyst does not change the position of equilibrium. This is because it will speed up both the forwards and backwards reactions equally, so therefore there'll be no change overall. We're going to start off by looking at what happens if we change the concentration of a chemical in an equilibrium. So for this equilibrium here, if we increased the amount of carbon dioxide, the system will want to reduce the amount of carbon dioxide, and it will do this by shifting to the right. Because if we want to reduce the amount of carbon dioxide, we're going to make more of whichever side doesn't have carbon dioxide on. So if we make more of the right, we're going to make more methanol and water, therefore we would make less carbon dioxide and hydrogen. If we change the question and we said if we decreased the concentration of carbon dioxide, the system would want to increase the concentration of carbon dioxide. And it would do that by shifting to the left. Because if we want to make more carbon dioxide, we're going to make more of the side which carbon dioxide is on, which is the left side, so we would shift the position of equilibrium to the left. So let's look at a worked example for this. Explain the effect of increasing the concentration of water on the yield of carbon monoxide. And it's always useful to annotate these questions, so we know we're increasing the amount of water, and we want to look at what the effect will be on the amount of carbon monoxide. So if we increase the concentration of water, the system will shift to the right to decrease the concentration of water, because there's no water on the right. So if we make more of the right side, we're going to make less of the left side, therefore reducing the amount of water. If we are shifting to the right, it means we're making more of everything on the right. So that means we're making more carbon monoxide, so we can say that the yield of carbon monoxide will increase, therefore answering the question. When looking at pressure, we need to know that the more molecules of gas we have on a certain side, that's going to increase the pressure, because there are more molecules of those gas bouncing off the containers of our reaction vessel, increasing the pressure. Whichever side has got the fewest molecules of gas on it, that's going to have the lowest pressure. So we're going to look at an example of that equilibrium again. This time, because we're looking at pressure, I've labelled on the state symbols of all the chemicals, so we know that everything we're looking at is a gas. There are 4 molecules of gas on the left-hand side, 1 molecule of carbon monoxide, and 3 molecules of hydrogen. And there are 2 molecules of gas on the right-hand side, 1 molecule of methanol and 1 molecule of water. So the side with the most molecules of gas will have the highest pressure, so that means the left-hand side has high pressure. That means the right-hand side is going to have the lowest pressure. So if we increased the pressure of this equilibrium, the system would shift to the right to decrease the pressure. And it would do this because the right side is the side with the fewest molecules of gas, therefore we know that means it has the lowest pressure, and we're trying to decrease the pressure. If the pressure of this equilibrium was decreased, the system would shift to the left-hand side to increase the pressure. Because the left-hand side is the side with the most molecules of gas, therefore the side with the highest pressure. So let's look at a worked example for this. We need to explain the effect of increasing the pressure on the yield of carbon monoxide. So the first thing we'll do is annotate the question. We want to know what happens to the yield of carbon monoxide. We're increasing the pressure. There are 2 molecules of gas on the left-hand side, 1 molecule of methane, 1 molecule of water, and there are 4 on the right hand side, 1 molecule of carbon monoxide and 3 molecules of hydrogen. This means that the left hand side is going to have the lowest pressure because it's got 2 molecules of gas, and the right hand side is going to have high pressure because it's got 4 molecules of gas. So if the pressure was increased, the system will shift to the left to reduce the pressure. And that's because the left is the side with the fewest molecules of gas on it. If we're moving to the left, that means we're going to make more of the left-hand side and less of the right-hand side. Since carbon monoxide is on the right-hand side, that means the yield of carbon monoxide will decrease. In order to discuss what happens when we change the temperature on an equilibrium, we need to remind ourselves what exothermic and endothermic reactions are. So an exothermic reaction is one which gets hot because it releases energy. If we look at the reaction profile of an exothermic reaction, we can see that the products are at a lower energy than the reactants, therefore there is a negative energy change, energy is given out or released. Endothermic reactions get cold, they take in energy. So again, if we look at the reaction profile of an endothermic reaction, we can see the products are at a higher energy level than the reactants, therefore energy has gone in, the energy has increased. So for this equilibrium, we've said that the energy change is negative, therefore the forwards reaction must be an exothermic reaction, because energy has exited the reaction, it's a negative energy change, therefore exothermic. And this means that the forwards reaction gets hotter. If the forwards reaction is exothermic, that means we know the reverse reaction is going to be endothermic, and that gets cold. So if the temperature of this system is increased, the system will shift to the left to decrease the temperature. And it does this because going to the left is endothermic, it takes energy in. If we're increasing the temperature of the system, going backwards to the left in the endothermic direction will make it colder. If the temperature of the system was decreased, the system would shift to the right to increase the temperature. And you would do this because going to the right is exothermic, that would release energy. So if we have decreased the temperature, we've made it colder, the system's going to want to do the opposite, which means going to the right, because exothermic will make it hotter. But we need to give our answer in terms of energy changes. For this worked example, we're going to explain the effect of increasing the temperature on the yield of carbon monoxide. So the first thing that we're going to do is label or annotate our equation. So we're looking at the yield of the carbon monoxide and we are increasing the temperature. The energy change is negative, therefore it's going to be an exothermic process in the forwards direction. So we can add that onto our equation, and it might be worth reminding ourselves that exothermic reactions get hot. If the forwards reaction is exothermic, this means that the reverse reaction is going to be endothermic, which we know gets cold. So therefore, if we increased the temperature, the system would shift to the left to decrease the temperature. Because going to the left is the backwards reaction, which is endothermic, which is going to take that energy in. And we also know the endothermic reaction will get colder, so if we're making the reaction hotter, we'll do the opposite, which is endothermic. If we're going to the left, we're going to make more methane and water, therefore making less carbon monoxide and hydrogen, so we can say that the yield of carbon monoxide will decrease.